Okay, so for question 3 in the tutorial this week, we have that 1 hour carbon monoxide concentrations in air samples from a large city have an approximately exponential distribution with a mean of 3.6 parts per million. And then we're given the PDF of an exponential random variable. In part A, we are asked to find the probability that the carbon monoxide concentration exceeds 9 parts per million during a randomly selected 1 hour period. So the first thing I'm going to do is I'm going to define a random variable y, which is going to represent our carbon monoxide concentration. So let y be the carbon monoxide concentration in a randomly selected hour. Okay, so part A, we want to find the probability that this concentration y exceeds 9 parts per million. So that's the event that y is greater than or equal to 9. And we want the probability of that. We can get this by integrating the exponential PDF that we're given above. So we want to integrate from y equals 9 to infinity because we want y greater than 9. And the PDF is lambda e to the negative lambda y. And we integrate with respect to y. Now, we've been quoted that our exponential has a mean of 3.6 parts per million, but as this exponential PDF is parameterized in the question, is in terms of the rate. And so we're given that the relationship between the rate, lambda, and the mean is that the mean is 1 over the rate, or 1 over lambda. So in this case, we're given the mean is 3.6. So our rate is going to be lambda equals 1 over 3.6. So we integrate from y equals 9 to infinity of 1 over 3.6, because that's our rate, e to the negative 1 over 3.6 y dy. So if we recall how we integrate an exponential function, we basically just divide by the constant that's multiplying y, which in this case is equivalent to multiplying by 3.6, e to the negative 1 over 3.6 y. And we're evaluating that from y equals 9 up to y equals infinity. Okay, obviously these 3.6s out the front are going to cancel and turn into just a 1. So what we're left with is, well, the first term will be e to the negative 1 over 3.6 as y tends to infinity. That's actually going to tend to 0. So 0 minus negative 1, because we've got negative 3.6 over 3.6 out the front, e to the negative 9 over 3.6. And if we go away and compute that, we should get 0.0821. So that is part A. Okay, so part B is very similar to part A, but all that really changes is that now we have a different mean for our exponential distribution. So part B is if a traffic control strategy reduces the mean to 2.5 parts per million, calculate the new probability that the concentration exceeds 9 parts per million in any randomly selected 1 hour period. So we're going to have y being this random variable, which is going to be the random concentration of carbon monoxide during a randomly selected 1 hour period, except now y is going to have this mean of 2.5 parts per million. So we want to calculate the probability of the same event, that is the probability that y is greater than or equal to 9. And exactly as before, this is equivalent to integrating the PDF from y equals 9 up to infinity. And then we had this exponential PDF. Remember the relationship between the mean and the rate. This exponential is parameterized in terms of its rate. So we need, but in the question, we were given the mean. So we need to convert from the mean to the rate. And so the rate, lambda, is actually 1 on the mean. So in this case, it's 1 over 2.5. E to the negative 1 over 2.5 again. Y dy. Integrating this, we'll get negative 2.5 over 2.5 e to the negative 1 over 2.5 y, evaluated at 9 and at infinity. Remember that as y tends to infinity, this exponential with a negative rate is going to tend to 0. And so the first term will be 0. And then take away the coefficient at the front here is actually just going to be negative 1. And then e to the negative 9 over 2.5. And if we go away and compute that, we should get 0.0273.